right, welcome to Chapter 2, Section 5. We've talked about real zeros, including rational and irrational zeros. So now we're going to look at our last type of zero we can have, which is complex zeros that are not real. And then now that we know all of the types of zeros, we'll be able to state the fundamental theorem of algebra. So in this section, we're going to learn two major theorems or review them. Hopefully you've seen them in algebra. We're going to look at complex conjugate zeros. So complex zeros and their conjugates, they always come in conjugate pairs, and we'll review what that means. And then factoring with real number coefficients. And why is this important? These topics provide the complete story about the zeros and factors of polynomials with real number coefficients. And remember, a lot of real world applications can be modeled by polynomials. So our two big theorems, I'm not going to make you wait for them, here they are. Our first theorem, the fundamental theorem of algebra. Hopefully you've heard this before, but if not, that's okay. Our fundamental theorem of algebra, or FTA as we will refer to it from here on out, is that a polynomial function of degree n has n complex zeros. That includes our real zeros and our non-real zeros. So remember, up to this point we were saying a degree 5 equation could have up to 5 zeros. Well, if we include our non-real zeros, then we have exactly 5 zeros. So the degree and the number of zeros have to be exactly the same, but that does not mean that a degree 5 equation has 5 x-intercepts, right? Because non-real zeros are not x-intercepts. They're complex. They don't show up on the graph, okay? Some of these zeros can be repeated. So I can have zeros with higher multiplicity than 1. That's what that means. If I have x squared as a factor, then x equals 0 would be a 0, and it would count as 2 of them because it has a multiplicity of 2. We'll go over examples of these. Okay, our second theorem is the linear factorization theorem, which says that I can take those zeros and write them all as linear factors, meaning x minus or plus a number. So if f of x is a polynomial function of degree n greater than 0, then f of x has precisely n linear factors, and we can write it as f of x equals a, our leading coefficient, times x minus the first 0 times x minus the second 0 times x minus the third 0, and so on for all n zeros, where a is the leading coefficient of f of x, and 0, 1, 0, 2, 0, dot, 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 all the way up to n are the complex zeros of f of x. The z sub I, so each 0, is not necessarily distinct. Some can be repeated. So that's what I was talking about. If I have something like a degree 5 equation, I can have f of x equals x squared times x minus 3 cubed. You saw something similar to this in a previous homework assignment. We have that x equals 0 is a 0, multiplicity 2. So degree 5, I still have 5 zeros, but 0, the number 0, counts twice. Our other 0, x equals 3, has a multiplicity of 3, so that counts 3 times. So I have 5 zeros, it's just that they are 0, 0, 3, 3, and 3. So they repeat, but there are still 5 of them, okay? And this counts as a linear factor because it would be x plus or minus 0. So when we're talking about linear factors, we just mean that all of the factorization should be completed, so I don't have any second or third degree polynomials as factors anymore. Okay, so let's look at polynomials with the complex case. So the fundamental polynomial connections in the complex case. We've been talking about this since the beginning of the year. We know that a solution, a root, a 0, they're all the same thing. Last video, we introduced that we can also now call them factors, because when we factor them out, that's how we get those zeros from a polynomial function. And then up till this point, we've also been saying they're always x-intercepts, but now that we're looking at complex numbers, such as potentially non-real numbers, then we can't call them all x-intercepts. They're only x-intercepts if they're real. So what do I mean? If I have x equals 3 plus 2i, how would you graph that as an x-intercept? Well, this could be an example of a complex solution, right? That is a value that would make our polynomial 0. However, and I just made that up. I just made it up to give you an example. So let's say that would make our polynomial 0. However, that will not be an x-intercept because there is no value on the x-axis of 3 plus 2i. That is a complex number, right? So it's still a 0, it's still a solution, it's still a root. We can still write it as a factor. However, now it's no longer an x-intercept because it's not a real number. Okay, so that's an important distinction now, is x-intercepts only include the real numbers. So let's do an example. Fundamental polynomial connections. Write the polynomial function f of x equals x minus 3i times x plus 3i in standard form, and identify the zeros of the function and the x-intercepts of its graph. So remember, standard form is where we have ax to the n plus bx to the n minus 1 plus ... and we can write this a bunch of different ways, and then we can have z x to the 0. Okay, so we can have all the different coefficients and all of the different degrees, but it's written out in standard form, meaning coefficient, degree, coefficient, variable rather, coefficient, variable, coefficient, variable, coefficient, variable. This is unfactored. Okay, so we have it right now in factored form. We want to write it in standard form. What do we have to do? Well, we have to distribute. Okay, so we can use the same rules as FOIL because these are both binomials. But if this was not binomials, we still have to distribute. And remember, I gave you that tool. You can do it as if it's a multiplication table when you're distributing to make sure that you distribute to everything. So first thing first, we're going to write it in standard form, meaning I've got to FOIL. So f of x equals, first thing, I'm just going to rewrite it. First is x squared outside plus 3ix inside minus 3ix, and last, now I have a negative 9i squared. Combining like terms, my middle two terms will cancel out. So I get x squared minus 9i squared. And this is where we're going to recall from algebra that I, the imaginary unit, is the square root of negative 1, right? And that means that I squared equals negative 1. Okay, this is where the imaginary unit came from. We said we need a number that when we square it, it becomes negative. And so we have this imaginary unit that doesn't act quite the same as our real numbers because when we square this one, it can be negative. We never want to leave I at a degree higher than 1. So we never want to leave I with an exponent. So since we have an I squared here, we're going to substitute that with negative 1. So this is x squared minus 9 times negative 1 gives me x squared plus 9. That is in standard form. Okay, that's one part of our answer. You might recognize that when we're using our complex numbers, if it has an imaginary part and no real part, so this was just plus or minus 3i, then we end up with a sum of perfect squares. And that's because what we end up with when we're foiling looks very similar to conjugates. Okay, and we'll talk about conjugates again in a minute. Okay, the second part we said is identify the zeros of the function and the x-intercepts of the graph. Okay, well, we're going to go back to the factored form to look at the zeros. Remember, if we have x minus k, then k is a 0. So from our first factor, we have x minus 3i. So that means x equals 3i is a 0. Our second factor, x plus 3i, then x also equals negative 3i. So we have two zeros here, plus or minus 3i. And then lastly, we want to talk about x-intercepts. Well, for this function, we had no real zeros. They were only non-real or complex non-real zeros. And since we said non-real zeros are not x-intercept, we have no x-intercepts. Okay, let's take a look at our next slide here. Complex conjugate zeros. So I've been using this word conjugate. I want to review what it means. So when we have a complex number, it means that I can write it in the form a plus bi, where a is a real number. This means element of the real numbers. That's a little epsilon. We've used that before. And bi is the imaginary part. So we have a real part and an imaginary part, and together they make a complex number. Now, if b is 0, when b is 0, then these are the real numbers. So our real numbers are still complex numbers. The real numbers are what we call a subset of the complex numbers. However, we can also have imaginary numbers, which is when a is equal to 0, we have imaginary. Now, a lot of times the word imaginary and the word complex are used interchangeably, but I will always try to refer to the numbers that are non-real, they're complex non-real, as complex non-real, because imaginary should mean that there's no real part. So if I have 2 plus 3i, this is not an imaginary number because it has a real part and an imaginary part. So this is a complex non-real number, or we could even just call it a complex number, okay? If I have something like 5i, that is an imaginary number. And if I have something like 7, that is a real number. So our complex numbers include the real numbers, they include the imaginary numbers, and they include our complex non-real numbers, which means that it has an imaginary and a real part. Okay, I won't be too stingy about using imaginary versus complex, but I will try to be precise when I'm talking about numbers. Okay, so let's read the text here. Suppose that f of x is a polynomial function with real coefficients. If a and b are real numbers and b is not 0, a plus bi is a 0 of f of x, then its complex conjugate, a minus bi, is also a 0 of f of x. So the conjugate means that the imaginary part switches signs. A plus bi and a minus bi. And that means that real numbers don't have formal conjugates, or at least they don't have complex conjugates, right? Because I can write this as 7 plus 0i, which is also 7 minus 0i, and both of those are 7. So you could kind of say the complex conjugate of 7 is 7, but nobody talks about 7 in that way because it's a real number. It's not a complex non-real number. So when we're talking about complex conjugates, we're really just talking about complex non-real numbers, and that includes imaginary numbers. So I can write 5i as 0 plus 5i, which means its conjugate would be 0 minus 5i. We can write that as plus or minus 5i. Okay, and when we're talking about zeros of a polynomial, if you found one of them to be imaginary or complex, then you automatically know a second 0, which is that complex number's conjugate. Okay, so if we're looking at f of x has a 0, x equals 2 plus 3i, then automatically x equals 2 minus 3i is also a 0. Okay, so as soon as you have one of the complex numbers as a 0, you know that its conjugate must also be a 0. Now this is important because if I give you a list of zeros and I give you one complex 0, then in order to have the complete polynomial function, you have to include its conjugate when you write it into factored form. So let's look at an example. Find the polynomial from the given zeros. Now we did one very similar to this last class where we took our zeros and we turned them into the factored form. And then we took that factored form and we turned it into a polynomial in standard form. Okay, so we're going to start with the -3. That means x equals -3, which gives us x plus 3 equals 0. Then we have 3 minus I, x equals 3 minus I, gives us x minus the quantity of 3 minus I. Now we can distribute that negative if we want to, but I suggest we leave it in complex form for now, and I'll show you why in a minute. And then we have our third 0 here, x equals 2 plus 5i, giving us the factor x minus the quantity of 2 plus 5i. However, we know that if I have a complex 0, I also have its conjugate, so we can write f of x equals x plus 3 times x minus 3 minus I, also the 0 of its conjugate. So this is still x minus, but instead of 3 minus I, it's 3 plus I. So think about in this list, we also have 3 plus I, and we also have 2 minus 5I. So we actually have 2 more factors that are just kind of invisible because they're the conjugates, so we know that they're there even if they're not listed. Then we have x minus 2 plus 5I, and its conjugate, x still minus 2 minus 5I. Okay, I want to point out a couple things. It's the sign in front of the I that's changing, not the sign next to the x. So when we're finding the conjugate, the sign next to the x stays the same. It's always x minus k. Even if k is a complex number, it's x minus that number. Okay, so now we have it in factored form. We want to write it into polynomial standard form, which means we need to distribute. Okay, and this is why it's helpful to leave it with a conjugate in parentheses, because then instead of distributing trinomials, I can treat it like I'm distributing binomials. Okay, so I'm going to hold on to the x plus 3, and I'm going to pair up the conjugate factors. And the reason that I want to pair up those conjugate factors is because I know that when multiplying conjugates, terms start canceling out. And so if I pair them up, that will help me simplify my polynomial in a much faster way than to distribute everything and then collect like terms. So we'll be able to start canceling like terms as we're still distributing. So first thing I'm going to do is FOIL this as if it's a binomial. X times x is x squared minus x times 3 plus I minus x times 3 minus I plus 3 minus I times 3 plus I. Okay, so that's my first pair of conjugates foiled. I haven't simplified yet. That was just writing out the multiplication. We'll do the same thing for our second pair of conjugates. That's x squared minus x times 2 minus 5I minus x times 2 plus 5I plus negative times a negative 2 plus 5I times 2 minus 5I. Let me make that look like a 5. Come on. Well, I can't draw the dot on the I for some reason. It's not working. So now we want to start simplifying. So we have equals x plus 3, still just hanging out in front. If I distribute the x, I get x squared minus 3x minus xi. Distributing the x again, minus 3x plus xi. There's our first pair of terms that will cancel out. Plus foiling, now I have a binomial times a binomial again. So that's 9 plus 3i minus 3i minus I squared. So there's another pair of terms that will cancel out. Notice I have an I squared, so we'll substitute that for -1 in our next step. We'll do the same thing here, x squared minus 2x plus 5xi minus 2x minus 5xi. Those will cancel out. Plus 4 minus 10i plus 10i. Those will cancel out. Minus 25i squared. Okay, so simplifying again in our next step, we're gonna cancel out those terms that we crossed out and also substitute our I squareds. So that's x plus 3 times x squared. 3x and 3x is -6x plus 9 minus a negative 1, that's going to become a plus 1, times x squared, minus 2x and a minus 2x is minus 4x, plus 4 minus 25 times negative 1 is going to become a plus 25. So x plus 3 times x squared minus 6x plus 10 times x squared minus 4x plus 29. Okay, from here it's polynomial multiplication. Now, it is long and you have to be organized. It's so important to be neat and organized. And that's why I think it's helpful to have that table, the multiplication table when you're doing this. So let's go ahead and start using that table. So I'm going to multiply my two trinomials first. X squared minus 6x plus 10, x squared minus 4x plus 29. So I get x to the fourth minus 6x cubed plus 10x squared minus 4x cubed plus 24x squared minus 40x plus 29x squared. 29 times 6 is 174 minus 174x plus 290. Okay, equals x plus 3 times x to the fourth is my highest degree, x cubed. I've got a negative 4 and a negative 6. That gives me minus 10x cubed, x squared. I have 29 and 24 and 10 more. So that's 63 plus 63x squared. I have negative 174 minus 40 more is minus 214x plus 290. And lastly, distributing again, I'm not going to use the box, the multiplication table for this one. I'm just going to distribute all my x's and then distribute all my 3's. So I'm going to do x3 as I go along. So we have x to the fifth plus 3x to the fourth. Now I'm going to write this in a way that I line up my like terms. So now I'm going to multiply them both to the negative 10x cubed. So that gives me negative 10x to the fourth minus 30x cubed. And then I multiply them both to the next term. So that's plus 63x cubed plus 189x squared on my next term. So that's minus 214x squared. And 214 times 3 is minus 642x. And then our last term, plus 290x plus 290 times 3 is 870. So now I have all my like terms lined up. I get x to the fifth minus 7x to the fourth plus 33x cubed, 189 minus 214 minus 25x squared, negative 642 plus 290 is minus 352x plus 870. And that is f of x in standard polynomial form in descending order. Now, we had it in factored form. In our first line, we had this polynomial in factored form, but that factored form included complex numbers. So if I wanted to write this in factored form without any complex numbers, notice we do have that step in our process as well, where we have a linear factor and two quadratic factors. And that is, there's another theorem that we can use that says any polynomial can always be written, even if it has complex roots, it can always be written with real coefficients in linear and irreducible quadratic factors. So that's our next theorem that we're going to look at on the next slide, which states that factors of polynomials with real coefficients. Every polynomial function with real coefficients can be written as a product of linear and irreducible quadratic factors, each with real coefficients. And so those irreducible quadratic factors can have irrational or non-real solutions. And so when we have polynomials that have irrational or non-real solutions, we can still write them with real coefficients, but we might have to have some of our factors as quadratic factors instead of linear factors. Remember that theorem we had at the beginning of the video where all of our zeros match our degree, or I should say the number of zeros match the degree, and those zeros can be written as linear factors. Well, if we want them to be real numbers in those linear factors, then sometimes the linear factors have to be multiplied together to get quadratic factors in order for those numbers to have real coefficients. So the key term here, the difference between writing them as linear factors and sometimes having to write them as quadratic, is when we want them to have real coefficients, meaning no i's. And even with irrational numbers, we can have linear factors with real coefficients, but a lot of times we'll write, for example, x squared minus 2 instead of x minus the square root of 2 times x plus the square root of 2, right? So this would be linear, and this would be quadratic. Okay, and the non-real solution we just saw, but I'll do a kind of simpler one, x squared plus 4. This is a sum of perfect squares, so it factors into x plus 2i times x minus 2i. So these would be linear, and again, that would be the irreducible quadratic form. Okay, so let's see if we can factor this polynomial as a product of linear and irreducible quadratic factors, each with real coefficients. So the first thing we're going to do, we look at this. This is a degree 5, so I can't use the quadratic formula. Does it look factorable? Actually, maybe. Let's try factoring by grouping. So what am I looking for? Well, in order to see if it's factorable by grouping, I'm looking for my first and second coefficient. Can I pair them up so that those coefficients kind of follow a pattern? So I saw this is 3 and this is 1, this is 24 and this is 8, this is 27 and this is 9, and those all make the same ratio. So that tells me that it might be factorable by grouping. So we have 3x to the 5th plus x to the 4th has a GCF of x to the 4th, leaving us 3x plus 1 plus, or minus 24x cubed minus 8x squared has a GCF. Always factor a leading negative. So that's 8x squared is my greatest common factor, leaving us 3x plus 1 minus 27x minus 9. GCF leading negative of 9. So that's 3x plus 1. Oh, that's nice. So now I have a GCF of 3x plus 1 that I factored out without having to use, but I could have the P over Q list and graphing it in order to find that 0 of x equals negative 1/3. Right? I found that by factoring by grouping. X to the 4th minus 8x squared minus 9. So now I have a 4th degree polynomial that I want to see if we can factor. So then the question is, are there two numbers that multiply to negative 9 and add to negative 8? Well, sure, 9 and 1. The bigger one needs to be negative. Okay, so this is 3x plus 1 times x squared minus 9 times x squared plus 1. X squared minus 9 is a difference of perfect squares. So we have 3x plus 1 times x minus 3 times x plus 3. X squared plus 1 is a sum of perfect squares, which means that is going to have complex, non-real roots. So we'll leave it in its irreducible form. So this is f of x in its factored form. Now, If you didn't recognize factor by grouping, then you can use the P over Q list. You'll get that whole list. You'll graph this. It'll do something like this. It will actually be at -3, +3, -1/3. So it'll look something like that. Okay. You'll find your points, test them. You can use synthetic division until you get those 3, and then your final quotient will be a 1, 0, 1 with a remainder of 0, giving you that x² + 1 factor. Okay. In this case, we didn't have to do that, but that whole process that we did from our last notes video and practiced in class, that whole process can still be used here. But don't forget about the other methods that you learned in previous years and that we kind of, we're still in the process of reviewing some of those, right? So factoring by grouping, those processes can still save you time. Okay, these last 2 problems I want you to try on your own. They will not necessarily be as straightforward as the last one that we did together. It's going to use more of the skills that we started last class with the P over Q list and everything, but your goal is to get it in that same factored form, okay? In class, we'll have a chance to do some practice and to go over questions and to go over the solutions for these 2 problems as well. If you have any questions, please email me. Otherwise, I will see you in class.